Let's start. So as everybody knows, we have the presentation and then questions from the audience and then questions from the committee. So Pranav has been here since 2019. Before that, he did his bachelor's at the University of Oklahoma. And here he has been working on the modeling of the cavitation in Vortex, the vertical flows, and also looking at the mixing in confined stratified flows. Okay, Pranav, floor is yours.
Okay. Hello, everybody. Thank you for joining. Today, I'll be presenting on, as Dr. Dabiri mentioned, cavitation in Vortex and mixing in stratified fluids. I'm thankful to my advisors, Professor Sadiq Dabiri and Professor Pavlos Vlahos, and also Professor Arzu Ardekani, because she's also on the project. So yeah, I will get started. One second. Yeah, so first I will present on cavitating bubble in Rankine vortex. So as you can see, there's a bubble here and it elongates cylindrically, and we will explore the bubble dynamics there. And then we will discuss rising bubble in confined linear stratification, and I will go into more details into that. Okay, so let's get started with the first project. So cavitation is present in various engineering applications, and it can hinder them through either noise, vibration, erosion, or reduced performance. So that's why we need to model it so that we can better predict it and mitigate the issues that arise from it. Cavitating vortices in general can be found in several applications as well, such as turbomachinery and blade surfaces. Now, so suppose if you have a vortex where the fluid is spinning, if that circulation velocity is really high, the pressure at the core can be very, very low and can even go negative. So in that particular scenario, if you have a certain nucleation site, such as a dust particle or a gas bubble present, it will cavitate. So the bubble dynamics in terms of the growth, splitting, and collapse for in vertical cavitation is not very well understood. So that's why we are studying this. And we also believe that studying vertical cavitation may also give us further insights into understanding turbulent flows. So I just want to point out that we are focusing on a fundamental problem with a single bubble, but in reality, there might be multiple bubbles that might be cavitating at the same time. However, our focus is more fundamental and looking at a single bubble. So Choi et al. In 2009 used axisymmetric conditions to predict how circular bubble like this may grow axially and become cylindrical, and they modeled the growth and the collapse at the separately. We also observed that there's supposed to be some re-entrant jets that are formed during the collapse stage of the bubble, which are also not explored. And Choi et al. In 2007 performed some experiments showing that this does happen, and they performed experiments to show that. So we perform three-dimensional simulations, and we use an all-mach solver on Basilisk, which is a multi-phase flow solver. We solve the conservation of mass and momentum equations, and along with the internal energy equation with the absence of thermal diffusion and mass transfer effects. We also have a color function in that which decides where the bubble is and where the fluid is. Finally, we close the system with a equation of state relating the pressure and density. So we use a Cartesian cubic grid and induce a Rankine vortex in it, given by these equations. So we have a line vortex, which kind of looks like this. I've plotted here the isosurface of the vortex, so you can see like how it looks like. And what we do is we initialize the the velocity conditions and the pressure conditions, and We also induce a small nucleation site or a small gas bubble at the center of the domain, and then we start our simulation like that, and then that leads to a simulation that kind of looks like this, where there's a small bubble that elongates axially and grows in this manner. So some of the important numbers that are important are the cavitation number, which represents how strong the vortex is, and the relationship between how strong the vortex is and cavitation number is negative. So the stronger the vortex, the stronger the vortex, the smaller the cavitation number is. We also have the bubble to vortex size ratio, and we have the aspect ratio, and we consider a constant surface tension in our simulation. So as I specified earlier, in a vortex, if the circulation velocity is really, really high, it can lead to very low pressures or even negative pressures at the core of the vortex. And if there's any nucleation site, it will grow. So there are different processes that are there, like growth, and then there's pinching at the center, then elongation and fragmentation at the end. However, here we will be only analyzing the growth part and leaving the rest for later. I mean, we have only analyzed growth till now. So the first thing we do is we induce a vortex in our simulation domain and observe how it diffuses over time without any bubble. So over here, I've plotted the pressure normalized by the atmospheric pressure along the center line of the domain, and as you can see, on the sides the pressure is equals to 1. However, near the center where we place our nucleation site, where we will place our nucleation site, the pressure is negative. And that is why the bubble cavitates. We can also plot the circulation velocity, and we see how it decreases, and how the pressure at the core basically increases from the negative that we induce. So now we go ahead, and now that we know how the vortex diffuses, now we go ahead and induce our bubble in it. So when we do that, as I mentioned, due to the negative pressures, the cavitation bubble grows very rapidly. So we plot the volume of the bubble divided by the initial volume of the bubble versus time in this semi-log plot. As we can see, the bubble is initially, I mean, the volume is just 1. However, depending on the several cavitation numbers, the volume can grow from being 1 to 2 or to 4 orders of magnitude higher than what it initially was. Moreover, if this phenomena or the volumetric growth is also highly dependent on the cavitation number, such that if the cavitation number is reduced further, we see that the difference is in 2 to 4, like it can be 2 orders of magnitude difference in the volumetric growth. So we conclude that the volume of the bubble is very dependent on the cavitation number. Moreover, we also look at the aspect ratio. Aspect ratio is important here because we are studying how the bubble grows axially. So at first, we see that in all the simulations, the aspect ratio is 1. That is, the bubble is circular. However, as we let the simulation run, that circulation, that aspect ratio decreases. That means it elongates. However, we get more elongation, or the aspect ratio is lower in lower cavitation numbers, or when the vortices are stronger. Then we also look at the shape of the bubble, which is plotted in this graph here. We see that so the column 2 and column 4 here is is at a time where the bubble volume is the maximum. So when we do that, we observe that at the second oscillation maximum, for this particular cavitation number of 1/75, we see that the bubble is still elongated with thinner ends. However, in other cases, we observe that in the other cavitation numbers considered, we observe that that there are actually three separate bubbles forming due to the elongation. The other thing that is interesting to notice is that the diameter at the center of the bubble is actually remains kind of constant. So you can see how the growth in radially for the bubble is kind of same. However, most of the growth takes place in the axial direction, in the direction of the line vortex. Finally, we also study the effect of how small that initial bubble that we place in the simulation domain is. So we start the simulation with several different sizes of the bubble, and we observed that even though the bubble sizes were different at which they were they started from, they lead to the same volumetric growth and the same aspect ratio. So what this shows is that that the bubble dynamics that takes place is actually independent of the initial bubble size that is induced in the vortex. So just to summarize what we found and what we have done, we solved the variable density Navier-Stokes equations to simulate cavitating vortex. The growth of the bubble we found is strongly dependent on the cavitation number and the vortex core pressure. We found that this growth is much larger in the axial direction than in the radial direction. And finally, we found that the size of the nucleation site is independent of the bubble dynamics that takes place. And as I mentioned at the beginning, we have only looked at the growth part, but there are other aspects that can be studied later, such as pinching, elongation, or fragmentation. So now I move on to the next project, which is on dynamics of a single rising bubble in confined stratified fluid. So just to give a brief overview of what we are doing here, we have density stratification. That is, the density is increasing as we go down. And what we do is we induce a small bubble through it, which has interesting wake patterns that we analyze, which eventually causes mixing, which is what I will be discussing later. But why is this important? Well, stratification is present in several natural bodies. For example, in a particular ocean, over here, the density is plotted versus the depth. And we observe that the density on the top is less and the density at the bottom is higher. So density stratification is ubiquitous and present in oceans and water bodies. And what that does is stratification actually hinders vertical mixing and affects the vertical exchange of heat, carbon, dissolved oxygen, and nutrients. And what we've also observed is that for the past 60 to 70 years, the stratification, which is quantified through the Brunt-Väisälä frequency squared over here, actually increases over time. So maybe this is a reason that could explain a decline in ocean oxygen concentration, reduced nutrient flux, and alteration of marine productivity and biodiversity. So in this particular scenario, usually bubble plumes are lots of small bubbles are used so that mixing, so that destratification can be done and to homogenize the fluid. So that is a really big motivation why we are doing this. Moreover, in oceans, saline stratification can trap myriads of pollutants as well, making the cleanup really difficult. So for example, in the density stratification, like cups or water bottles could be stuck, and rising bubbles are, when bubbles rise, they actually create a vertical flow, and which brings the any particles or sediments to the top so that it can be collected easier. Rising bubbles can also be used to create a bubble curtain, as you can see over here, so that if there's an oil spill, you can restrict the movement of that oil spill so that it can be more easily collected from the surface of the water. Finally, in bubble column reactors, bubbles are used to mix several chemical species without any mechanical agitation. So in this particular scenario, like a sparger might be used because of its mechanical simplicity and low cost. So in oceans, we've also observed that stratification actually blooms the population of cyanobacteria, which can cause serious health issues such as conjunctivitis if it comes in uh, contact with human eyes. So that is why we have to study this. So now looking at the literature a little bit more, Ganesh and Dabiri found that mixing efficiency actually increases when the stratification is higher or when the Froude number is lower. In several experiments, and I'm just citing one here, people have shown that rising drops, rising bubbles, or falling spheres actually experience enhanced drag while going through that motion. Rising bubbles through stratified fluids or through homogeneous fluids cause mixing through three different mechanisms, through turbulent dispersion, diffusion, and wake transport. However, it is really difficult to study all three at the same time, which is why we perform our experiments in confinement in a really thin channel, because that allows one to focus solely on the wake transport effects and understand the mixing process that takes place due to the wake transport in much more depth, rather than tackling all the three problems at the same time. So the other thing is that no current experimental or numerical work has been done in a bubble rising in stratified fluids. The closest work that comes to it is a rising non-oscillating drop in stratified fluids. A lot of work has been done in falling spheres in stratified fluids, or rising bubbles in homogeneous fluid is done. So that's why there is a need to publish this and analyze the flow. There are several unanswered questions as well, such as how does a single bubble wake evolve in confined stratified fluid in comparison to its homogeneous counterpart? What are the notable fluid structures that are observed, and how do they scale with the Froude number, which is what quantifies the stratification? And what is the is there a significant out-of-plane velocity component in stratified fluid as it is observed recently in homogeneous fluid? So these are some of the questions, specific questions that we plan to answer in the next 10 minutes or so. So to just share what our experimental setup looks like, we have a thin channel, which is about 2.5 millimeters wide, with a height of 70 centimeters and breadth of 40 centimeters. We create density stratification. So density is increasing as we go down. That is done through a double tank method, where in one tank, we have high salt concentration, and in the second tank, we have pure deionized water. And by controlling the flow rate through the two pumps here, one can control how the stratification will look. And people have proven that by making the flow rate through pump 2 twice the of pump 1, you can get a linear stratification, as you can see. So as the height decreases, the density increases. Moreover, we illuminate our field of view from an LED from the front, and we record our images through 3 cameras, 2 of which are used for stereo reconstruction, and we record at 500 hertz. And the center one is used to calculate bubble properties. Our field of view is 11 times 16 diameters of the bubble. That provides enough resolution to perform and analyze everything in the experiment. We perform our experiments at 3 different stratifications, which correspond to approximately Froude numbers ranging from 42.8 to 22.6. And we also perform our experiments in homogeneous fluid just to see the comparison of what are the differences in the flow structures that take place. So first thing we do is we analyze the out-of-plane velocity component. So in Rudet et al. In 2011 performed some experiments in a Healy-Shaw cell, which is a confined channel. And by emptying that cell, and they analyzed how the pressure-driven flow velocity looks, they analyze that there is very close, they get good agreement with 2D PIV at Reynolds number of 200. They also analyze the flow in front of a rising bubble with potential flow theory, and they found good agreement. So based on that, they came to a conclusion that 2D PIV provides depth averaged velocity that can be used for these experiments. However, they did not consider any flow near or in the wake of the bubble to come up with any conclusion. So recently, in 2021, 10 years later, Pavlov et al. Showed that there is a three-dimensionality in the flow that occurs until one diameter from the bubble. So what we do is, for our experiment, we plot for the homogeneous case here. So I'll describe the plot here. So we have a bubble right here, and we plot the velocity along the line AA and line BB over here. And when we do that, we find and we plot all the velocity components along these lines. When we do that, we find that about 2.5 diameters away from from where the bubble is, and the bubble, as you can see, is over here where the velocity is 0. About 2.5 diameters away, the velocity, or the VZ, out of plane velocity, becomes 10% to that of the bubble velocity. So that's when basically it becomes less significant in comparison to the other velocity components, as can be seen here. And the other velocity components are much more dominating. So, and we found a similar trend in stratified fluids as well, that about 2.5 diameters away from the bubble, the out of plane component is more than 10%, and after that it becomes less again. So we come to a conclusion that the out of plane velocity component for our experiments is important for 2.5 diameters away from the bubble. Another interesting thing to notice is that in stratified fluids, the horizontal component, the horizontal velocity component, dampens much faster than in the homogeneous fluid, and we can see that that the velocity in both homogeneous and stratified fluid is positive because of the vertical flow that the bubble creates. So to provide a better understanding of like the dynamics that is going on, so you can imagine there is a bubble and the density in the field of view is increasing. So as the bubble is rising, it actually carries, the wake of the bubble carries the heavier fluid to the top. And when the gravitational force is large enough, this displaced fluid actually falls down, giving rise to a reverse buoyant jet. So when we plot the velocity at the center of the field of view, and we plot that vertical velocity over time, we observe that initially the velocity is 0. Then there's a positive velocity because as the bubble comes up, it pushes the fluid around it. And then the velocity changes, and then it becomes positive. This positive velocity shows the vertical flow that the bubble creates. And finally, the velocity becomes 0 and then becomes negative, and before going into quiescent flow again. Now, what we can do is, from all the data that we have captured, we can actually find the time scale for which this flow reversal takes place. So we do that over here, which we call as tau wake, and we normalize it by the bubble diameter divided by the velocity of the bubble. This is a good time scale because this represents at what time scale the vertical flow is happening, depending on the bubble velocity. And we found that there is a good agreement between this time scale that we have found and the Froude number, and we come to a conclusion that, and the R squared here is 0.92, and we come to a conclusion that that this non-dimensional flow reversal that takes place is actually is proportional to how strong how strong the stratification is. So for stronger stratifications, that is for lower Froude numbers, the flow reversal takes place faster. So now we want to look at how the vortices develop in the flow a little bit more. So as a rising bubble oscillates while going up, it sheds these counter-rotating vortices in the background, as you can see over here. So the bubble just went up, and this blue region represents counterclockwise rotating vortices, and the red region represents clockwise rotating vortices. And you can see in homogeneous fluid, the vortices that are, the blue vortices stay on the left side and the red vortices stay on the right side. However, in stratified fluids over here, we observe the opposite trend, that vortices do get released in the same pattern. However, later on in time, they actually switch directions that we will be analyzing in the next slide. So from the shears, because we are analyzing our flow in a confined channel, there is a shear stress that is acting from the wall, which attenuates the vorticity that takes place. So as I mentioned, the vortices shed remain on either side in homogeneous fluid. However, they change directions in stratified fluids. And yeah, so now we can look at the coherent structures in more detail. So for over here, I've plotted for homogeneous fluid, the vortex centers that we detect over time. And in homogeneous fluid, they stay on either sides. However, in stratified fluids, they change direction. So for example, this green one over here at an intermediate time travels to the right, and then it later on in time, because of the reverse buoyant jet, because when this displaced fluid that is carried up by the bubble, when that comes down due to gravity, the coherent structures basically come down as well. So now what we can do is we can track these vortices for homogeneous fluid and for stratified fluids and see what we observe. So when we do that in homogeneous fluid, when we plot the x position of the vortices versus time, we observe that in homogeneous fluid, we observe what we expect, that vortices basically stay on either side and kind of move outwards. In the vertical position versus time, we observe that the bubble creates a vertical flow, because of which the vortices get carried up, and once they reach a certain position, they stay there constantly. However, in stratified fluids, we observe a different phenomena, that these vortices are released and they basically switch directions, as you can see, and then they continue to move on opposite trends. As well as in the y direction, the bubble still creates a vertical flow, because of which the vortices get carried up. However, because of the reverse buoyant jet that takes place behind, the vortex basically come down again, and they basically travel down in the field of view. So next thing we want to look at is how are the vortices that are being released by the bubble decay. So if these vortices decay according to a law, or according to this exponential law discussed in Roig et al. In 2012, they will follow a slope of 12. And now we will see what slope our results show. So for homogeneous fluid, when we plot the vorticity in this semi-log plot versus time, of vorticity versus time, we observe that there is a linear decrease in vorticity. That means these vortices that are being that are released attenuate exponentially, but it looks linear because of the semi-log plot. And the slope here is actually minus 20, given in the legend over here. So what this means is that there's an additional mechanism besides diffusion that is taking place that attenuates the vortex, which is the shear stress that acts from the wall. So that is why the decay that takes place of the vortices happens at a rate faster than what we expect purely through diffusion. Things get more interesting in stratified fluids when when we see that when the vortices are released, they again follow this -20 slope. That means the shear stresses from the wall is acting on them. But then something really interesting happens, and they become constant, followed by when the flow reach becomes more quiescent. The slope that that the vortices follow is the diffusion. So what happens in the center region? So, well, the vortices naturally, because of diffusion, will decay over time. Now, you can imagine that if the vorticity in a vortex continues to stay the same, that means an additional energy, some kind of energy is being added into the system for the vortex to continue the rotation. So this happens, this is exactly the time scale where the reverse buoyant jet that forms behind the bubble takes place. So this an extra energy production term actually comes from the reverse buoyant jet that takes place behind the bubble. And we believe that it is because of this reason, and because of the reverse buoyant jet, we observe that there is higher mixing that takes place in when a bubble rises in homogeneous fluids. So just to conclude and analyze and mention everything that we have done, we perform a stereo PIV experiment on a bubble rising in confined stratified fluids. We found that there's a significant out-of-plane velocity component that is significant in both homogeneous uh, and stratified fluids, close to 2.5 diameters from the bubble. We found that the time scale of the flow reversal is proportional to the level of stratification. That is, the flow reversal happens faster, but stratification is higher. And finally, we found that there's a reverse buoyant jet that forms behind the bubble rising in stratified fluids that leads to a persistent motion of coherent structures, which eventually leads to higher mixing. And thus, in oceanic or industrial applications where there might be stratified fluids present, results from our finding can be used uh, to mix those fluids. And rising bubbles could be employed or incorporated to mix any kind of stratification that might be present. So thank you, and I'll open it up for any questions that the audience might have.
Thank you, Pranav, for the presentation. So we have time for questions from the audience. If you have any questions, you can just unmute, and if you would like to turn on your camera and talk.
Say Pranav. So
Yes.
this is my question.
Yes.
In everyday life, what practical application for safety would this research contribute to? I mean, it could be automobile or just anything. I mean, water in your house, just some way to having some awareness of the increasing pressure or cavitation might apply.
So cavitation is difficult in a normal household kind of application. But for example, like there are some, I think, shrimps that will actually use cavitation to stun their prey, and so that so they basically send the shock wave that stuns the prey, and so that they can eat it. So that might be like one natural application where that is there. But I think in household application, cavitation might be difficult, if I'm not wrong.
Okay.
Thank you.
You are.
Can you expand more on some of the environmental pieces, like on the plastics being pushed up to the surface? That was interesting to me as an environmental studies background.
Yeah, so there's this company, I think in Denmark, that is working on this like a river cleanup thing. I can try to go to that slide. One second. So yeah, there's this company, I think in Denmark, that is using rising bubbles to actually clean up the waste or pollutants from the river. So what they do is they create a line of like bubble injectors at the bottom, and as the river flows, the rising bubbles kind of creates a vertical flow and also a curtain that brings the pollutants to the surface. And by having it at an angle, you can basically, through the motion of the river, collect it in the corner over here for cleanup. So that is something that, yeah, they're working on.
Thank you.
Thank you for asking.
Any other questions from the audience?
I'm curious, nobody has any questions on the actual physics that he presented?
I think I've presented this work to everybody, so everybody's asked their questions previously.
I could ask a quick question. If you can
Yes,
go to your
sure.
conclusion slide.
For which work?
For your second work.
Okay.
Actually, probably you can go to slide 20. Yes.
Yes.
So here in the velocity.
Yes.
Yeah. In the velocity field plots, the vector plots.
Yes.
So we have that green circle signifying the bubble, right? So we don't
Yes.
have the velocity field computed at that location. That's
Yes.
why we see a 0 here in
Yes.
the side plots. Okay.
Yes. That's why you see a 0 here, 0 here, 0 here, and 0 here.
Thank you.
Thank you.
Okay, so if there are no other questions, I would like to ask the audience to leave the room so the committee can ask their questions.